So today in class we found that elements are quite interesting on their own, but it's really cool when we can start to combine them, and that's the heart of chemistry, is the ability to combine all the elements that we know of to make different things, to make the different molecules and compounds that make the world go round. We can obviously take a material like hydrogen and a material like oxygen, and we can put the two of them together, and we can make a substance that's crucial, that is essential to life in water. But my question is, how do we know what the formula for water is? Why do we know it's H2O? That's the central focus of this video, 4.3, the compound concept. So we start with this dude named Avogadro. Avogadro was a chemist that worked a lot with gases and came up with a law, and he said for a law, equal volumes of gases have the same number of particles if those gases are at the same pressure and temperature. And this is essentially the hypothesis he puts forth, and his hypothesis is thus proven to be true. He says two samples of gases with the same pressure and temperature contain the same number of particles. So if we take a look at this, we can look at a visual. We have three different gases. You're familiar with all three of these gases. You've got helium on the left, and nitrogen in the middle, and methane, which is essentially natural gas, on the right. And if we look at the conditions of these gases and compare that to Avogadro's hypothesis, we'll see something interesting. The pressures of all three are the same, so check mark, right? Equal pressures. The temperatures of all three are the same, so again, check mark. Temperatures are the same. And actually, for good merit, the volumes are also all the same of these materials. And what we notice now is that the number of molecules is the same for every single one of the gases. It's a huge number, 6.02 times 10 to the 23rd, which you'll eventually find out is a very important number in chemistry. But they're all the same for the helium, nitrogen, and methane. In fact, the only thing that's different about these gases is the mass of the samples. So if I took each one of these samples and I put it on a scale, the masses would actually read something different for each of the gases. I wonder if you can think of why that might be. Go ahead, pause the video. Try to think of it. All right. So maybe you came up with the fact that the helium atom is small. It's a tiny little atom. The nitrogen atom is a big molecule. It's actually two molecules put together. And then the methane molecule is actually in between. So it's about the size of the molecule that gives the mass of the particular gas that we're talking about. All right, so let's get back to the topic at hand, Avogadro's hypothesis. Again, he says that two samples of gas, no matter what they are, if they're at equal pressures and temperatures, they will contain exactly the same number of molecules. All right, so how does this help us understand compounds? So we got an apparatus here that they call a Huffman apparatus. Essentially, it's like electrocuting water. So you got a battery, a big old battery there on the left, and it's hooked up to some nodes. And these nodes are run through the bottom of some test tubes. And what happens is you go through a process called electrolysis. You take water, and by running electricity through it, you break it apart into its constituent atoms. And you can see from the bubbles, we can see bubbles that are rising from the nodes there and there. You can see from the bubbles that they're filling up the test tubes with a particular gas. Now what's interesting, if we take a zoomed in look, is what happens when this process is completed. Okay, this is about the end of the process. And when we do some investigation on the two gases that make up the test tubes, the top of the test tubes, we find that this gas right here is actually pretty explosive. It doesn't allow us to breathe, so it actually kills mice. It's kind of nasty. It's odorless. It's colorless. This gas right here allows a candle to burn. And allows us to breathe. So it doesn't kill mice. Doesn't kill mice. So we take that gas and we fill a little chamber and we put a mouse in there and the mouse runs around and has a good old time. So it doesn't kill. Nice. Okay. So we give these two gases names, and we actually call this guy right here, maybe you guessed it, we call that oxygen, and we actually call this one, well, at first we called it something like phlogiston, but eventually we called it hydrogen. There we go. Good. Now, what do you notice about those two gases? Well, hopefully you notice there's more of this stuff on the right than there is this stuff on the left. And in fact, if you kind of, I don't know, if you did a little ruler analysis, I think what you might find is that there's about twice as much hydrogen as there is oxygen. And doesn't that make sense? So now if you look for your formula of water, and you have H2O, what does that mean? Well, it means for every one oxygen, you have two hydrogens. For one oxygen, you have two hydrogens. There we go. So this is kind of Avogadro's hypothesis proven through experiment. He was able to take water and break it apart. Now, if the formula for water were HO, what would we expect to see? Well, we would expect these two columns of gas to fill up at exactly the same rate. Why? Well, that's because of Avogadro's hypothesis. Because the formula is not HO, it's H2O, the hydrogen fills up twice as quickly as the oxygen. Again, this is still leading to Avogadro's hypothesis. Okay. So let's build off of Avogadro's hypothesis. We actually have to go back a little bit further in time, before Avogadro's time, to talk about the law of constant composition, formed by a guy by the name of John Dalton. And Dalton realized that elements don't just stand on their own, that they can combine to form different types of compounds. One of the first compounds that was measured, it was called calx, which is just a combination of mercury and oxygen, and they found that by heating it, you could drive the oxygen on. So it was known that the calx had to be a combination of more than one element. And Dalton's law of constant composition simply says this, that a given compound always has the same relative number and types of atoms. This is known as his law of constant composition. It's pretty simple now that we think of it. I've got a whole bunch of different compounds here on the right side and some molecules. Let's take the water molecule. Water always, H2O always has the same relative number and types of atoms. It doesn't matter if I get that water molecule from Lake Michigan, or if I get it from the Atlantic Ocean, or if I get it from my water bottle. Every single one of those water molecules will have exactly the same formula. He says the same thing for all other molecules: nitrogen dioxide, carbon dioxide, chlorine, nitrogen, oxygen, hydrogen, nitrogen monoxide, and all of the other types of molecules that we can think of. They all follow this idea of the law of constant composition. Now let's think about this idea in the terms of masses instead of just the relative numbers of atoms in a compound. It brings us to another law. This one's known as the law of definite proportions, or Prost's law. This says that a specific compound always contains the same proportions of elements by mass. And I'm going to show a pretty cool demonstration for this one tomorrow. Here's the idea. Water, no matter what water molecule, again, if it's from the Atlantic Ocean or Lake Michigan, is always 8/9 oxygen and 1/9 hydrogen. So it contains the same proportion of elements by mass. So let's say we wanted to make water. We know it consists of hydrogen and oxygen, and we know that it consists of 2 parts hydrogen and 1 part oxygen. So let's just say we had 2 liters of hydrogen and 1 liter of oxygen. If we combine those two with a little bit of heat, we will form exactly 1 liter of gaseous water. Now let's say we try to get sneaky and we say, wait a minute, I want to form more water. So let me go ahead and add in more oxygen. Now I have 2 parts hydrogen and 2 parts oxygen. Aren't I going to form more water? No. You'll still form only 1 part of gaseous water. The ratio stays the same. The ratio to form the water stays exactly the same. And it's right here, what I'm circling in green. parts hydrogen, 1 part oxygen to form 1 part gaseous water. So, what about the remaining oxygen? Well, it's leftover. It comes out at the end. It's like if you're baking cookies, and the cookie recipe calls for 2 eggs. But in your refrigerator, you've got 4 eggs. You can't just put in the 2 extra eggs and think you're going to have the same type of cookie when you're all said and done. You're going to not use those 2 other eggs. You'll have leftover eggs. This oxygen, well, that's your leftover eggs. One more law. The law of multiple proportions. The law of multiple proportions says this.
Cyril Organ, please come to the office. Cyril Organ, to the office, please.
If 2 elements form more than 1 compound, the ratios of the masses of the second element, which combined with the fixed ratios of the first, will be a whole number. It's kind of a multiple. Let's take an example. 2 compounds that you're familiar with. Check out the bottom of the page. Carbon monoxide, deadly. Carbon dioxide, you're breathing that out right now. Now, both of these compounds are very similar. They both contain carbon and oxygen. And we can go even a step further by saying they both contain 1 carbon atom. They differ in the amount of oxygen atoms that they have. Now, let's say we have 1 gram of carbon. We've got that on top. And we react that carbon with some oxygen. Some of the sample will form with 1.333 grams of oxygen. Another part of the sample will form with 2.666 grams of oxygen. To give the 2 different types of carbon and oxygen containing compounds that we see down here. Now, what's important to notice? The numbers. Notice that carbon dioxide will have twice as much oxygen as the carbon monoxide by mass. That's the law of multiple proportions. We can do the same thing with nitrogen oxide compounds. If we split up this little chart that I have into 2 sides, and we just look at the things to the left of that white line, we see nitrogen monoxide and nitrogen dioxide. Now, nitrogen has a mass of 14. We'll figure that out later. But it has a mass of 14. If we double the amount of oxygen, you'll notice that the mass of the oxygen also doubles. So, all we need to know, we don't need to know the formula of the nitrogen oxide or the nitrogen dioxide, of this or this. If we know these ratios, we should kind of know what the molecule should look like. In order for those ratios to be true, I got to have twice as much oxygen. Now look to the right side. This is a little bit different, a little bit more complicated of an idea. Instead of having nitrogen, 1 nitrogen atom, we have 2 nitrogen atoms in each one of those compounds. But again, look at how the mass of the oxygen changes. It changes proportionally. We only have 1 oxygen, so there's 16. That must be the mass of 1 oxygen atom. Here we have 2 oxygens, so 32, the mass of 2 oxygen atoms. And here we have 5 oxygen atoms, so 80, the mass of 5 oxygen atoms. Again, this is the law of multiple proportions. If 2 elements form more than 1 compound, the ratios of the masses of the second element, in this case, oxygen, which combine with the fixed ratios of the first element, in this case, nitrogen, will be a whole number ratio. All right, that's the compound concept.